Our next topic is called points of inflection. So a point of inflection is the point where a function changes concavity. So the concavity either switches concave up to concave down or concave down to concave up. So we're going to draw a couple examples of points of inflection. In our first graph we have concave up and then it switches to concave down right at this point right here. So that would be your point of inflection. So we had concave up to concave down. Okay. Another example, here we have concave down and then it switches to concave up. So here would be your point of inflection. Here was concave down and here was concave up. So our point of inflection. Another example here. Okay, so the point of inflection will be right here where we switch from concave up to concave down. Now one thing you're going to want to notice here is that if we drew the tangent line at the point of inflection, the graph crosses over from one side to the other side at that point of inflection. Okay, and we can see that that's true here and it's true here as well. Now, if f of c is a point of inflection, then either f double prime of c equals 0 or f is not differentiable at x equals c. So here's what we mean by that. So if this was our c right here, we would know that f double prime either equals 0 or does not exist at these points. Okay, so here and right here. Let's look back at some of our other examples because we were dealing with concavity. So let's go back and we'll look at this one. So remember, a point of inflection is where we switch from concave up to concave down or concave down to concave up. So in this graph right here, it's where we switch from concave up to concave down. So this would be a point of inflection right here, and our c value would be -1. Now you can see at -1 what was happening to our second derivative was our second derivative equaled 0. And we see there was another point of inflection here because we switched from concave down to concave up. So that's also a point of inflection. And we can see that the second derivative was also 0. So always two things that have to happen. The second derivative has to be 0 or not exist, and we have to switch from concave up to concave down, or concave down to concave up. Alright, so we're going to try this first one together here. It says determine the points of inflection and discuss the concavity. So they really go hand in hand. So again, we need to find our second derivative. So our first derivative is 4x cubed minus 12x squared. And then our second derivative is 12x squared minus 24x. So we need to find where this does not exist or it equals 0. Well, it's going to exist everywhere, so we'll just set this equal to 0. And we can take out a 12, so we're left with x squared minus 2x. And we can factor out an x. We're left with x minus 2. And so our second derivative equals 0 when x equals 0 or 2. So can we automatically say that a point of inflection happens at x equals 0? No, because we have to make sure and test the concavity to see that it actually switches at these x values. So we still have to find our whole concavity here. So we have our interval -infinity to 0 and 0 to 2 and 2 to infinity We'll pick some test values here. Let's try -1. So -1 squared is positive, times 12 is 12, minus 24 times -1, so that's plus 24, and so that is 36. We get a positive second derivative, so the conclusion is concave up. This interval, we could try 1, so let's try f double prime of 1, and we're going to get 1 squared is 1 times 12, so 12 minus 24 times 1, we get -12 here. And so the second derivative is negative. We say this is concave down. And here, let's just try 3. So we get 3 squared is 9. 12 times 9 is 108. Minus 24 times 3, which is 72. 108 minus 72 is 36. So we can see that that's going to be positive, and so we get concave up. Okay, so our possible points of inflection are right here at 0 and then at 2. And what makes them points of inflection is if it switches from concave up to concave down at that point. And you can see that it does here. So here we had concave up on that interval, and then here we had concave down on this interval, and then here it switches back to concave up. So because that happens, we actually get a point of inflection at 0, whatever the y value is, and at 2, whatever that y value is. So if we just plug this back into our function, 0 to the 4th minus 4 times 0 cubed, that equals 0. And if we plug 2 in, okay, we'll get 2 to the 4th minus 4 times 2 cubed, and that is -16. So we do get our 2 points of inflection right here. All right, let's try our next example. Here we have x to the 4th. And if we want to determine the points of inflection, we would go, let's see, f prime of x is 4x cubed. And we'd get f double prime of x, which is 12x squared. We set that equal to 0. And so x equals 0. So the point that is a possible point of inflection is here at 0. Graphically, it looks like this is going to be concave up and then concave up. So it doesn't switch. But let's go ahead and test out this interval, -infinity to 0 and 0 to infinity. So here we can just try -1, so f double prime of -1. Here we get, let's see, so that becomes +1, that becomes 12, which is positive, meaning this is concave up. And then let's try f double prime of 1. So that's going to be 1 squared times 12, that's also 12, also positive, so we get concave up. So if we had concave up to concave up, this is not a point of inflection because the concavity did not switch at 0. Alright, so that is how to determine points of inflection of a function.